Hello everyone and welcome to our channel, Mootechie. A special welcome to all the dairy technologists and students with us today. We're going to explore the fascinating process of penicillin production, a key topic in industrial microbiology. Now let's look at the structure of penicillin. The general structure of penicillins consists of several key parts. There is an acyl side chain attached to a core ring system. This core includes a beta-lactam ring and a thiazolidine ring. The diagram also shows the atomic arrangement with carbon, nitrogen, hydrogen, and a carboxylic acid group labeled as C, N, C, H, and COOH. Understanding this structure is important because the beta-lactam ring is essential for penicillin's antibacterial activity. Moving on, we will see the microorganisms used in penicillin fermentation. Out of various species of the fungus Penicillium, two main species are used, Penicillium notatum and Penicillium chrysogenum. Among these, Penicillium chrysogenum is the high-yielding strain most widely used in production. The production strain is often improved through mutation using agents like X-rays to increase yield. After strain improvement, it is crucial to carefully maintain the strain because Penicillium chrysogenum is genetically unstable. Different preservation techniques are used. For example, a spore suspension may be mixed with a sterile, inert support like soil or sand and then dried. Spores can also be stored under liquid nitrogen at -196 degrees Celsius in a frozen state. Another method is lyophilization or freeze-drying of the spore suspension in an appropriate media. Next, we explore the preparation of the inoculum. The chief goal here is to develop a pure inoculum in adequate amount and in the fast-growing phase for the production fermenter. This involves several sequential steps. First, a starter culture, which is stored cold, is transferred to an agar plate to allow growth. After growth on solid media, one or two growth stages in shaken flask cultures create a suspension that can be transferred to seed tanks. These seed tanks are made of stainless steel and are designed to provide an ideal environment for the production strain. They contain all necessary nutrients, including growth factors like vitamins and amino acids. The seed tanks have agitators for continuous mixing and a pump to deliver sterilized, filtered air. After about 24 to 28 hours, the content of the seed tanks is transferred to the primary fermentation tanks. The main fermentation tank is a larger version of the seed tank, containing the same growth media and providing a proper growth-promoting environment. During fermentation, the microorganisms excrete large amounts of the antibiotic. All biological parameters like temperature, pH, aeration, and agitation must be properly maintained. In the following section, we discuss the key biological parameters and raw materials. The pH should be maintained near 6.5. The temperature should be between 26 and 28 degrees Celsius. Aeration is provided by a continuous stream of sterilized air pumped into the fermenter. Agitation is achieved with baffles that allow constant mixing. Raw materials are primary requirements for designing the fermentation broth. The broth contains all elements necessary for microorganism growth, including a carbon source, a nitrogen source, a mineral source, precursors, and antifoam agents if needed. Let us go further and examine the carbon source. Lactose acts as a very satisfactory carbon compound when used at a concentration of 6%. Other carbohydrates like glucose and sucrose may be used, but they must be provided at a slow feeding rate. Complex and cheap sources like molasses or soy meal, which contain lactose and glucose, can also be used. These materials serve as a food source for the organisms. The nitrogen source is another essential compound for metabolism. Ammonium salts such as ammonium sulfate, ammonium acetate, ammonium lactate, or ammonia gas are used. Sometimes, corn steep liquor is used as a nitrogen source. Additionally, minerals are necessary for proper growth. These include phosphorus, sulfur, magnesium, zinc, iron, and copper, which are generally added in the form of water-soluble salts. Coming up, we learn about precursors. Various precursors are added to the production medium to produce specific types of penicillin. The most important naturally occurring penicillin is Penicillin-G. Depending on the precursor added, the type of penicillin produced can be changed. For example, if phenylacetic acid is provided, Penicillin-G will be produced. If hydroxyphenylacetic acid is provided, Penicillin X will be produced. Phenoxyacetic acid is used as a precursor for Penicillin-V production. When corn steep liquor is used as a nitrogen source, it also provides phenylacetic acid derivatives, so it is widely used in the production of Penicillin-G. Now let's look at antifoam agents. Antifoaming agents such as lard oil, octadecanol, and silicones are used to prevent foaming during fermentation. When choosing raw materials for penicillin manufacture, 3 points should be kept in mind. First, ensure abundant growth of mycelium. Second, achieve maximum accumulation of penicillin. Third, facilitate ease of extraction and purification of the antibiotic. Following this, we notice the composition of the production medium. The components are given in percentages. Lactose is used at 3.5 to 6%. Calcium carbonate at 1.0%. Corn steep liquor at 3.5%. Glucose at 1.0%. Phenylacetic acid at 0.5%. Sodium hydrogen phosphate at 0.4%. And an anti-foaming agent, edible oil, at 0.25%. It's important to note that lactose is generally absent in the inoculum medium because it induces penicillin production, but can retard the growth of the production strain. Moving on, we explore the recovery process. The recovery of penicillin is carried out in 3 successive stages: removal of the mycelium, countercurrent solvent extraction of penicillin, and treatment of crude extracts. At harvest, the fermentation broth is filtered on a rotary vacuum filter to remove the mycelium and other solids. Phosphoric or sulfuric acids are added to lower the pH to between 2 and 2.5. This transforms the penicillin into its anionic form. The broth is then directly extracted in a Podbilniak countercurrent solvent extractor using an organic solvent like methyl isobutyl ketone, amyl acetate or butyl acetate. Filtration must be done carefully to avoid contamination with penicillinase-producing organisms, which could destroy the antibiotic. This step must be rapid because penicillin is very unstable at low pH values. Penicillin is then extracted back into water from the organic solvent by adding potassium or sodium hydroxide to form a salt. The resulting aqueous solution is acidified again and re-extracted with methyl isobutyl ketone. These shifts between water and solvent help purify the penicillin. The solvent extract is carefully back extracted with sodium hydroxide, and from this aqueous solution, various procedures cause the penicillin to crystallize as sodium or potassium penicillinate. The resulting crystalline salts are then washed and dried. Finally, the final product must pass rigorous government standards. Spent solvents from the process are recovered for reuse. Sometimes the crude extract is treated with charcoal to eliminate pyrogens, and it may be sterilized. Sterile vials are used for packaging the antibiotic, either as a powder or suspension. For oral use, it is tableted, usually with a film coating. The product must satisfy all government criteria before being marketed. Thank you for joining this detailed session on penicillin production. We've covered the microbial strains, fermentation process, medium composition, and the complex recovery and purification steps. Understanding this process highlights the incredible effort behind producing this life-saving antibiotic. Thank you. See you in the next class.